I'll come back to the area under the curve, area between curves, I should say, area between curves, podcast 2. And so I just finished simplifying this here. So kind of to show you what I did. So I plugged in the 15. If I plug in the 0, I'm going to get 0. So I just put a minus 0 there. And then we plugged in the 18 minus the 15. Right? And so we had to do that for both sections. And hopefully there's no mistakes on anything. Let's find out. All right, so we have 4/3 times 1/2 square root of 15 all cubed. Right? And so then we have minus 0. So then I come over to this one. All right, so the 4/3 times the square root of 1/2 x cubed, I plug in the 18. Right? And the 1/2 is cubed as well. So we have minus then 18 divided by 2 squared. At this point, I distributed the negative sign, so it's going to be a minus and a plus, right? Excuse me. And then we're going to have minus, so that's going to be a plus 15 times 18. And then we'll have to distribute the negative. And I did that, that parentheses goes with the radical there. So we have a minus 4/3 times 1/2 times 15 square root of 1/2 times 15 cubed, and then we have a plus 15 times 15. So I just distributed the negative, so I didn't have to keep writing it. All right. So I noticed here that we have a positive and a negative. 4/3 1/2 times 15. Cube, that one there. It's underlined. That cancels each other out. So I do have a 4/3. Half of 18 is 9. 9 cubed is 27. So we have 4/3 times the square root of 27. And then we have 18 squared divided by 2 would be a minus 162. We've got the 15 times 18, that'd be 270. And then the 15 times 15 would give us 225. Right, so that's going to give us a total of 4/3 the square root of 27 plus 333, which is approximately 339.9282. Hopefully, there's not any other areas there. I think the hardest thing sometimes is just plugging them in, especially if you've got some complicated numbers to deal with, like the square root of 1/2. Right. So if you see any mistakes, let me know, and then we'll go through it, and we'll fix my arithmetic. Let's continue on. Actually, there's not that much to this podcast. I think there are 5 pages left. So we want to find the area of the region bounded by x plus y squared equals 4, x minus y equals 2. When you see a y squared, just assume you're going to be solving for y. So we're going to have, I'm going to move the x, so we're going to have 4 minus x. And then we're going to have x equals, wait. Other way around. So let's move the y squared. So we have x equals 4 minus y squared. And then we'll move the y, so we have x equals y plus 2. All right, so that's our equation. Right? So we're going in terms of y. So it means that we're going from top to bottom. That works, go right to left, because it's in terms of y. That works out well. You can see that top to bottom does not work out so well for us because green will go to green. You don't want that. You just don't want that. Go the other way. So we're going to have those horizontal strips, and our rightmost curve is the parabola 4 minus y squared. And then we're subtracting the line y plus 2. All right, so now to find, we already were told our points of where they intersect, 0, -2, and 3, 1. So we don't have to really worry about that. And so we're using the y values, so that means -2 and 1. Right? And you get that, also could just get that by setting it equal to, setting each part equal to each other, right? Because they're both equal x, so we're just substituting 4 minus y squared for one of the x's, right? And then 2 plus y, and then just move everything over. 0 equals, this would be y squared plus y. We have 2, and then we have minus 4. So that's going to be negative 2, and this is going to be 0 equals y plus 2, y, oops, and I put an x in there, y plus 2 and y minus 1. So you can see we're going to have negative 2 and 1. Right, as our variables. Right, as our limits there. So from negative 2 to 1, right, so we've got the right curve, 4 minus y squared, and then we're subtracting, and I distributed the negative, so I don't have to worry about it later, minus 2 and minus y dy. So we're just going to, we can combine, may as well combine that 4 and minus 2 to make it a 2 minus y squared minus y, although it's perfectly fine to integrate them both separately and then combine afterwards. So we have 2 minus y squared minus y dy. So when we integrate, that becomes 2y minus y cubed divided by 3 minus y squared divided by 2, evaluating from negative 2 to 1, and we're just going to plug in. So we plug in the 1's, and then we subtract the negative 2's. So we have 2 times 1 minus 1 cubed divided by 3 minus 1 squared divided by 2, and then we're subtracting 2 times negative 2 minus negative 2 cubed divided by 3 minus negative 2 squared divided by 2. All right, so we're going to have 2 minus 1/3 minus 1/2. We'll have 2 negatives, that's going to be a plus 4. We're going to have 3 negatives, that's going to be a minus 8/3, and 2 negatives, that's going to be a plus 2. So we can add the 4 and the 2 and the 2, and that's 8. The negative 8/3 and the negative 1/3 is negative 9/3, that's just 3. And have we seen this problem before? 4.5. Did I just do the same problem twice with a different graph, or is it just 2 graphs that have 4.5 as an area? I'm not sure. Well, anyway, you get to review it again. All right, so here we have 3 lines and an up-close section of those curves because it might be hard to see. So we have the red line, f of x, is just x. Right, it's going to have a slope of 1. You can see I didn't even put in values here. This is a terrible graph, except it's good enough. The red graph there is y equals negative x. So, or excuse me, the green graph is y equals negative x. So it has a same thing but a slope of negative 1. So red graph is y equals x, green is y equals negative x. And then we have the blue graph there, y equals 1/2 x minus 1. All right, and notice they change places. So first the red one's on top, and here's my close-up, you can see right below it. The red one's on top, and then the green one's on top. But always the blue is on the bottom. So we have 2 different ones. We go from red to blue, and then we go to green to blue, and we subtract. So we're going to have red minus blue plus green minus blue, and subtract from one another. All right, so we need to find the intersections between red and blue. The 2 lines that are intersecting are the red line is x and the blue line is 1/2 x minus 1. So first of all, I smartly got rid of the 1/2. I multiplied everybody by 2. So 2x equals x minus 2. So subtract x from both sides. X is negative 2. Is that one boundary there? Right? So the red and green, where they intersect, is going to be the upper value for the integration, and that's where we'll switch over to green, being the top one. All right, so we have x and negative x. All right, so if I add x to both sides, x equals 0 and x equals 0. So they intersect right at the origin there at 0. So that's going to be the upper. So we're going to go from negative 2 to 0, red minus blue. I even color-coded. How about that? And then 1/3, and then we had to solve for the other boundary point. So it's where the green and the blue line intersect. So it's where negative x intersects with 1/2 x minus 1. Again, I multiplied everything by 2. So we have negative 2x equals x minus 1. I decided to subtract for some reason instead of just adding, probably because the negative 1 was all by its, would have been is with the x. So we have negative 3x equals negative 1, x is 1/3. That's where the other 2 lines intersect. So we're integrating with respect to x, which means right top minus bottom, and the variables of integration, our values are going to go from left to right. Notice the top function switches at x equals 0. So we start off with red minus blue. The red is on top. and that's from -2 to 0. At 0 it switches, and now the green is on top. So we have green minus blue from 0 to 1/3. Right? And these are the steps that you would take to do this. And if you put forth this much detail, you will get these correct. Right? Where students make errors is where they don't put forth the detail and they make careless errors. And then, of course, once in a while something's a little bit tricky. But really, most of these aren't too bad. So we're going to have x minus 1/2 x minus 1. Right? So I distributed the negative sign. So we have x minus 1/2 x plus 1 dx. And that's going to be from -2 to 0. And now I have negative x, and again I distributed the negative sign. We'll have -1/2 x plus 1 dx. All right, so combined to my like terms, I have 1/2 x plus 1 dx from -2 to 0, plus -3/2 x plus 1 from 0 to 1/3. All right, so we integrate. So we're going to, x1 increases by 1, and we'll divide. So it becomes x squared divided by 2 becomes 1/4 x squared. Plus x, and we'll evaluate that from -2 to 0. And then we increase the exponent, that's going to be a squared, and we're going to divide by 2, so that'll be -3/4 x squared plus x from 1/3 to 0. All right, so if I plug in the 0, I get 0. 0 minus, I'll have 1/4 -2 squared plus a -2, and then we'll plug in the 1/3, we'll have -3/4 times 1/3 squared plus 1/3, and if I plug in the 0, I'm going to get a 0. All right, so now I'm going to distribute the negative. So I have 4 times 1/4, and then multiplied by -1. I have -1, and then plus 2. All right, and then -3/4 times 1/3 squared. That is a square, so that'd be 1/9. And the 3's cancel, so that's going to be -1/12. And then we have plus 1/3, and then we don't need the -0. So the 1/12, I just changed it all to 12. So -1, oops, sign error. And even when you try to be really careful, somewhere, oh, no, I don't have a sign error. Oh, silly me. -1 plus 2, that's 1. So 12 twelfths plus 4 twelfths, that's the 1/3, and then minus 1/12 gives us 15 twelfths, and this is perfectly correct. All right, so let me know if you have any questions in class. I think I have got maybe 2 more slides. All right, so in general, if you have a vertical cut, all right, it's going to be top function minus bottom function. That's a dx, right, and it should be solved for x. So don't use it if you've got a y squared. And then a is your lower limit, b is your upper limit, and a is going to be smaller than or equal to b. Of course, if they're equal, we have no area whatsoever. And if we have a horizontal cut, that means we're dy. This time it is solved. Oh, my goodness. Solve for y, solve for x. I just said don't use it if you have a y squared, because you won't be able to solve for y. So this is solved for y, and this is solved for x. All right, and so notice that it's the other variable. So if it's solved for y, we're integrating with respect to x. If it's solved for x, we're integrating with respect to y. And you can notice what time it is. So I'm a little tired after teaching. This is like a 7th class. And this is my closing. So I told you this one was a little shorter. And you're going to set up an integral or integrals for the area of each of the shaded regions. You do not have to evaluate the integrals. I just want you to set it up. So number 1 is pictured there. You're just going to set up the integral. So I need to see, are you integrating with, is it going to be a dx? Is it going to be a dy? Okay, which way is it going to go? And I need to see your variable of integration, all right? So, your points of integration. What's your boundaries? So the boundaries need to be there, all right? And set this up correctly. That's all you need to do. So pause the tape, and you can complete the closing. I don't think this is too difficult, and I'll check it tomorrow. This will show me at least if you can set it up, because quite honestly, if you can set it up, that's half the work, all right? And have the correct intervals. All right, so see you in the next podcast. Bye.